This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The fourth lecture is broken into 3 parts. Lecture-04A covers the definition of the extended phase graph basis. The learning objectives for this lecture are to define the extended phase graph basis, to write the transformation to and from the EPG basis, to give the EPG basis coefficients for simple cases, and to define the magnetization represented by simple EPG coefficient sets. We first review the complex vector format. So here we will define mxy, the transverse magnetization, as mx plus I times my, which is something that you've probably seen before. The forward transformation is shown on the left in the orange, where the mxy formulation is represented as a matrix times our real valued mx, my, mz vector. On the right, you see the reverse transformation here. So you're already familiar with this transformation from the previous lectures. We now give an overview of extended phase graphs. It is very common in MRI to use a gradient that dephases by an integer number of cycles across a voxel. We can represent this in simulations by using many m vectors, or a 3x(n) array, and we can use the simulations that we saw in the previous lecture. However, instead we can actually use a Fourier basis. The advantages of this are that operations can be done in the Fourier domain because of linearity. This is a very compact representation of numerous magnetization vectors, and the linear phase from a gradient is a simple shift. So this is a picture of a single cycle of twist due to a gradient, and we'll see how this is represented using this Fourier basis. So in extended phase graphs, we look at the varying transverse magnetization and longitudinal magnetization in a voxel. We do a Fourier transform where we assume that if we have quantized gradients, again that induce an integer number of cycles, that we can represent the magnetization as a Fourier series. Note that the parameter z is between 0 and 1 across a voxel. It actually can be in any of the 3 directions. It is possible to derive this from multiple dimensions simultaneously, but for most of this course we will focus on 1 dimension at a time. If we do this, we can write that the transverse magnetization is the sum of basis coefficients given by the f's multiplied by basis functions, which are these twists. A lot of the work for this has been performed by Jürgen Hennig and other members of his lab, including Matthias Weigel, so you can reference this paper and other papers. We can show graphically the EPG basis. First, the f sub n are the Fourier basis coefficients. We refer to f plus as positive twists. So we have 0 for no twist, 1 for 1 twist, 2 for 2 twists, and so on. We can transform these Fourier coefficients back to the magnetization using a simple Fourier transform. The transverse bases are simple phase twists, but the sign indicates the direction. So we can now look at the f minus states, f minus sub 1, f minus sub 2, and so on. And now we can write this transverse magnetization again as a Fourier series, but we carefully pull out the DC coefficient here. The longitudinal coefficients are called z sub n, and the basis here are sinusoids instead of twists. And these look like this: z0, z1 is a single cycle, and z2 are multiple cycles. The transformation is again more or less a Fourier transform with some scaling, since this is a one-sided Fourier transform. So we will look at examples of these shortly. First, let's look at the transformation from the magnetization to the EPG basis, since this is actually quite easy to remember. So if we start with the F plus states, these correspond to a positive twist, and these are a simple integral over the voxel of the magnetization multiplied by a complex exponential. The F minus states are the same integral over a voxel, but of the complex conjugate of the magnetization multiplied by the same complex exponential. The Z states are similarly the same integral over a voxel, but of the mz times the same complex exponential. So you notice that there is some redundancy. We use the F minus sub n states, and we can use a two-sided representation, which I'll mention a little bit later, where we have F plus with a negative n subscript, and take the complex conjugate of this. So in this case, we can use the F plus and F minus coefficients of order where n is greater than or equal to 0, or we can just use the F plus coefficients and use positive and negative n. And notice on the right, we can write this whole integral much more compactly. So we can actually write the forward transformation very compactly, even though it's an integral, so perhaps a little less intuitive than the backward transformation. So a brief note on how we represent these graphically. There are many options for this. So when we show a twist like this, we're actually using up-down for the voxel dimension here. So we say voxel dimension times 2, because this goes from -1 to 1, but our EPG definition actually goes from 0 to 1, or equivalently from -0.5 to 0.5, as long as it's over an integer number of cycles. But we keep it this way so that things look good in the plot. We can show the MXY twist looking from above, where we're simply just using the colors. And we're actually not worrying about the location within the voxel, we're just looking at the distribution here. And this actually works for most cases. We can also show a 3D view, and again the colors show the spread here. We can look at the Z states, where we actually plot the voxel variation along the MX, or the X direction here. So now you see a sine wave along X, or a cosine, sorry. We can use simpler axes, where we actually take away the white and just show the spins. And we can do this in 2D or 3D. And again, the 2x voxel, don't be confused by that. It just helps the arrows to look good in these. Remember, the voxel dimension could actually be along the physical x, y, or z, or some combination of these. So really, there are lots of ways to represent this, and I hope it will become clear as we come through. So let's do a quick example question based on what you've seen so far. Don't worry if you have to look back to answer these questions, but I encourage you to try to work these out and do a little bit of practice on this, although the definitions are always available for you. So if we have mxy is equal to e to the 4 pi I z, what are the EPG coefficients? Notice that this is just transverse magnetization here. So there's a hint. Here are the definitions for you, and these are the definitions I find most useful here. So if you look at this definition, you can see the answer. The answer is f plus sub 2 is 1. And you can see this from the definition of mxy just by choosing the coefficients that would work here, given the range of n and given the what we're summing over here. So this is what we call a positive twist of 2 cycles. So now let's try mxy is equal to I times e to the 4 pi I z. So now we've rotated the magnetization twist. So we still have 2 cycles of twist, but we've rotated it. So it's now along my. And so we've simply taken that coefficient and multiplied it by I, again using this definition. So let's look at another case. mxy equals cosine 2 pi z. Okay, so here we recognize the fact that a cosine can be written as a sum of a positive and negative complex exponential, and we can find the coefficients f1, f plus of 1 and f minus of 1, and they're both 1/2 for a cosine. So we picked the easiest example first. Okay, now what if we rotate this so that the cosine is now along y? And now, based on our definitions again, we see that again we have a magnitude of 1/2 for both of these, and we just have to get the I and the sine right so that this is now a cosine along y. Notice that the cosine, by the way, the center, the 0 point is halfway along here, so this is in fact a positive cosine, as is the one on the left. So this brings us to another example. Now we're looking at the longitudinal magnetization and asking what are the EPG coefficients for mz equals cosine of 2 pi z. Again, the hint shows the forward and the backward transformations. So the answer here is z1 is equal to 0.5, and this can be seen from the definition at right. Remember, it's a it's a one-sided representation, so we double this coefficient when we convert it, and we take the real part, which leads to the cosine. Next, let's look at mz equals sine of 2 pi z. And again, from the definition at right, you can see that z1 is equal to minus 0.5 times I. And looking, you can see that this is how we generate a sine function. Now let's look at a combination where we have a transverse magnetization and we have a longitudinal magnetization. And the transverse magnetization is a complex exponential. So now you see that we have a single cycle of phase twist. So this corresponds to f plus of 1 of 0.5. But we also have longitudinal magnetization, and this is in the z0 state, so it's not doubled in the transformation. So we have z0 equals 0.5, and this gives us basically a dephased cone, if you will, but it's really a dephased disk because the longitudinal magnetization is actually constant across the voxel. Here's another example. Now we have mxy is equal to cosine of 2 pi z, and mz is equal to sine of 2 pi z. So think about the shape here. Notice that mxy is real valued. So what we have here is a dephased disk in the mx-mz plane. The disk looks like this at right, and the way this is represented is with f plus of 1 equals 0.5, f minus of 1 equals 0.5, and z1 is equal to 0.5i. This gives a disk of basically radius 1 here. Notice again the z1 coefficient is actually doubled because of the one-sided representation for the longitudinal magnetization. We're now going to look at the reverse, where we start with the EPG coefficients, and we look at what is the magnetization that corresponds to those coefficients. So often we're going to see our EPG coefficients written in a matrix like this. Here, the F positive coefficients are along the top row, the F negative coefficients are along the second row, but notice that the leftmost element is the same as the complex conjugate of F plus 0. This is the same as F minus of 0, according to the definition we showed earlier. The bottom row are the longitudinal coefficients, Z. I call this matrix Q for no particular reason, but I tend to use that throughout. Now mostly, to calculate the magnetization, we're just going to do this inverse Fourier transform. We've already seen these relationships quite a bit. So let's look at some examples here. And I'm going to really build this up from the basics and go reasonably quickly through these. So we have the case where all of the magnetization is along Z. There's no variation across the voxel. So our EPG coefficient matrix is just 0, 0, 1, and our magnetization is actually just 0, 0, 1. If all the magnetization is along MX, we notice the relationship between F plus 0 and F minus 0. So both of these are 1s, and this corresponds to MX. If all the magnetization is along MY, we now have an I and a minus I, again complex conjugates, that gives us MY. The graphics here show the magnetization graphically that corresponds to these EPG coefficients. Now there are also two cases here that are interesting. First of all, this is not allowed because these must be complex conjugates, and this is not allowed because Z0 must be real valued, and this is because the longitudinal magnetization is real valued. We can now look at the case for transverse magnetization of order n equals 1. So we can have one dephased cycle. So if we have basically F plus of 1 is 1 in the Q matrix here, this corresponds to M being a dephased disk with Mx as cosine 2 pi z and My as sine of 2 pi z, which looks like the picture shown. We can reverse that cycle if we actually swap the 1 down into the second row here. And this is the same as taking the complex conjugate of mxy. So you see that the disk is now flipped about the mx axis. Now we can also rotate this disk so that it is centered now along my, and in this case f plus of 1 is simply I, and that gives this disk that's been rotated from the above configuration. So now we'll look at the longitudinal magnetization of order n equals 1. Remember from this one-sided definition to double the Zn coefficient effectively. So if we have Z1 equals 0.5, this corresponds to a cosine variation of mz across the voxel. And for a sine wave variation of mz, we have Z1 equal minus 0.5 times I, and this can also be seen from this definition. So let's look at another example here. We're going to see this a little bit in the next lecture, but if we have a refocusing pulse that rotates the magnetization about the mx axis here, we have start with a dephased disk here. We're just looking at the first order states, or n equals 1. Now notice the notation is a little bit different here, but we start with this dephased disk and just worry about the amplitude of these states. So we're actually going to start on the left in the f plus 1 state, and we're going to end in the f minus 1 state as we actually flip this disk over like a pancake. So watch the titles of the plot change as we play this video, and you see that as we rotate this disk, the populations in these states vary. I'll play that again. I can actually drag this video, and as you see the populations changing, you see the longitudinal magnetization increases and then decreases, but you also see that the components from the positive and negative states, as these vary in amplitude, we have a dephased disk in the positive and negative direction, and the combination of these gives you this sort of elliptical shape when you look down on the magnetization. We'll look again at this example later. Another thing to talk about are these graphical representations again, and we can actually write these representations in this graphical form where they're actually laid out the same way as that Q matrix. So here we have magnetization states with a certain amplitude, and the amplitude is plotted along the top and the bottom. We have the F0, we have F1 and F2, and these are really the F minus of n states here. we have the 3D view of the magnetization. Because of the redundancy of showing the F0 state here, we can show a 3D view here, and then we can show the longitudinal magnetization here. Now we can also do this by showing these as twists, which might be useful for some configurations or variations. And here we've shown the MZ with the variation along the MX direction across the voxel, just for the graphic. There are also some variations, as mentioned. Finally, I'll just remind you that there are some variations in how EPG bases are presented. So we've shown, and we try to stick to the case where we have F plus and F minus coefficients for the transverse magnetization. So we essentially have two one-sided sets of coefficients. You can instead use the F plus n's where n is positive or negative, and then you'll actually have a simpler reverse Fourier transform. There are also some schemes that use a two-sided longitudinal representation where the n can be positive or negative, and again the definition becomes a bit simpler in this case here. So there are different reasons and advantages and disadvantages to these different representations. We're going to try to stick to one of them just for consistency, but just be aware that the others exist. So in summary, extended phase graphs use the transverse magnetization, its complex conjugate, and the MZ. And remember, the magnetization is mx plus I times my for mxy. The EPG coefficients that we typically use are f plus sub n, f minus sub n, and z sub n. The forward transform is an integral over the magnetization, over one of those three magnetizations shown, to give the corresponding coefficient of the same color here. The reverse transform is a sum over the transverse coefficients and over the longitudinal coefficients. The EPG states can be represented graphically as different variations over a voxel. So there are different ways to do this that we've started to show and that we'll see in the next lectures. So the next question is, using the EPG basis, what are the operators on that EPG matrix for precession, gradients, relaxation, and excitation?